We now come to a new topic, and this is about the Riesz Representation theorem. So this Riesz Representation theorem is another method to define measures on topological spaces which have some nice properties. So let me recall what we have seen so far in terms of methods of constructing measures. So first we have seen on RD, we have seen the Lebesgue measure M on defined on the Lebesgue sigma algebra L of RD. So this is the collection of Lebesgue measurable sets. Lebesgue measurable sets, and this forms a sigma algebra. So this construction was via the Lebesgue outer measure, and we defined a concept of Lebesgue measurability with respect to this Lebesgue outer measure. Lebesgue measurability. So we saw that the sigma algebra of Lebesgue measurable sets, when we restrict the Lebesgue outer measure on this sigma algebra, it has some nice properties, namely it has the countable additivity property for disjoint collections of Lebesgue measurable sets. So this was specifically on RD. Then on abstract measure spaces, we saw two ways of defining a measure. So the first one was via given an outer measure mu star, then the Carat-Theodory extension theorem gives you a measure mu on a sigma algebra B, where rather I used the notation C mu star of x, where C mu star of x was the sigma algebra of Carat-Theodory measurable sets. And these were precisely the ones that satisfied the Carat-Theodory criterion. The other way was to use the Hahn-Kolmogorov metrization, Hahn-Kolmogorov extension theorem, and this was the input data for this was given a pre-measure mu naught on a Boolean algebra B naught on x. Then the Hahn-Kolmogorov extension theorem gives you a sigma algebra B which contains this Boolean algebra B naught and a measure mu on B such that mu restricted to B naught equals mu naught. So this was the extension theorem, because this measure mu extends mu naught. And we saw that both these methods for abstract measure spaces, namely the Carat-Theodory extension theorem and the Hahn-Kolmogorov extension theorem, can be applied to RD, and when we use the Jordan measure as a pre-measure on Jordan measurable Boolean algebra, Boolean algebra of Jordan measurable sets, then we get back the Lebesgue measure. And similarly, when we use the Lebesgue outer measure and use the Carat-Theodory extension theorem, then we again get back the Lebesgue sigma algebra. So Carat-Theodory measurability, so let me put this as a remark, that Carat-Theodory measurability with respect to the Lebesgue outer measure M star is equivalent to Lebesgue measurability. So this means that the sigma algebra of Lebesgue measurable sets is the same as the sigma algebra of Carat-Theodory measurable sets with respect to the Lebesgue outer measure. So this we have already seen before. And in terms of, so this is the first remark, and the second remark is that in terms of, if we take mu naught is the Jordan measure on B naught being the Boolean algebra of Jordan measurable sets, then again the induced measure that we get from the Hahn-Kolmogorov extension theorem is the Lebesgue measure again. So in this sense, these two approaches, when applied to RD, gives you back the Lebesgue measure when you choose the Jordan measure using the Hahn-Kolmogorov extension theorem, and when you choose the Lebesgue outer measure using the Carat-Theodory extension theorem. So now the Riesz representation theorem, where it fits in this scheme, the Riesz representation theorem fits in this following way. So if we take X to be RD, then the following map, the map which takes a function in L1 of RD with the Lebesgue measure to its Lebesgue integral dm, this is a linear functional. So linear functional means that, so let me define what is a linear functional. Linear functional so if V is a vector space, let's say a complex vector space, a linear functional is a linear map lambda from V to C, meaning that if alpha, beta are complex constants and V1 and V2 belong to V, then we have lambda of alpha V1 plus beta V2 should be equal to alpha lambda V1 plus beta lambda V2. So this is the well known linearity property, and of course we have seen that the Lebesgue integration is linear in this sense, because if you take integral alpha f plus beta g for two functions f g in L1, we have that the Lebesgue integral of alpha f plus beta g is equal to alpha times the Lebesgue integral of f plus beta times the Lebesgue integral of g. So this is an example of a so the Lebesgue integral is an example of a linear functional over L1 of Rd. So let me put this as a remark, that the Lebesgue integral functional is a linear functional on L1 Rd with the Lebesgue measure. Now this Lebesgue integral also has the nice property of non-negativity, meaning that if f is a positive function in L1 Rd, then the integral of f is a positive number, or rather a non-negative number. So this property of the Lebesgue integral functional makes it into what's called a positive linear functional. So let me define what is a positive linear functional. Let sigma be a subspace of L1 Rd, be a linear subspace, then a linear functional lambda which takes elements of sigma and gives you back complex numbers is called positive if we have for f positive in sigma, lambda f is positive in C. So this implies lambda f is positive in C. So with this definition, we see that the Lebesgue integral is a positive linear functional. So we have defined, or rather we have obtained a positive linear functional from our measure, which was the Lebesgue measure on Rd. So the Riesz representation theorem gives a converse, meaning that for an appropriately defined positive linear functional on a suitable, so let me call it lambda, on a suitable linear subspace sigma of L1 Rd, we can recover the Lebesgue measure. So in our case, the appropriately defined positive linear functional lambda will in fact be the Riemann integration functional, and sigma, we take sigma to be the space of continuous compactly supported functions on Rd. So these are functions Rd to C such that f is continuous with compact support, and lambda, when you define lambda from Cc Rd to C given by lambda f equals integral over some big box B, or let me write Rd here because fx dx. So this is the Riemann integral, functional, which is also a positive linear functional. And when we define a lambda with this, we get back via the Riesz representation theorem, we get back the Lebesgue measure. So this is yet another construction of the Lebesgue measure, and of course we get back also the sigma algebra of Lebesgue measurable sets. So in fact the Riesz representation theorem works not only for Rd, it also works for any locally compact Hausdorff spaces. So let me recall what are locally compact Hausdorff spaces. So the definition for locally compact Hausdorff spaces is as follows. So a topological space X, let's say we should already assume Hausdorff because this is something you know already. A Hausdorff space X is called locally compact if every point has a neighborhood whose closure is compact. So this is what a locally compact Hausdorff space is. Of course, as an example, we already have Rd. This is due to the Heine-Borel theorem, because if X belongs to Rd, then Bxr, the open Euclidean ball centered at X with radius r, this has compact closure for each r positive, closure for all positive r. So this is due to the Heine-Borel theorem. So we see that Rd is locally compact. Similarly, the n-dimensional complex vector space, this is a locally compact Hausdorff space. And any metric space, any compact metric space is locally compact and Hausdorff. Of course, it is Hausdorff because it's a metric space, but since we are assuming compactness, then it is also locally compact. So locally compact Hausdorff spaces enjoy some nice properties, and the main one is that the Riesz that we will be interested in is that the Riesz representation theorem holds for locally compact Hausdorff. So I will abbreviate locally compact Hausdorff by LCH. So it holds for locally compact Hausdorff spaces X. Before I go to the statement and proof of Riesz representation theorem, we will have to recall some basic facts about locally compact Hausdorff spaces. Now, a good reference for this material that we shall use is Folland's book. Section 4.5. So in chapter 4, section 4.5, this is on locally compact Hausdorff spaces, and because we won't have time to give all the proofs, so basic facts like Urizone's lemma, we have to go back and recall for yourself and see the details in this book.